Okay, thank you very much. Yeah, I mean, the weather is nice today as well, so obviously I was completely wrong about the statistics for, for the weather in Vienna. Okay, so yesterday you heard some musings, let's say, about information theory and how it might be connected to diffeomorphism. So maybe a bit less philosophical talk today. And I think Alice gave us a very, very good introduction to information geometry, its connection to statistics. So I will talk more today about the connection to hydrodynamics and certain PDEs. Okay? So, and then hopefully towards the end, let's see, I'll kind of connect back to information geometry. Let's see. So let's talk about diffeomorphisms and the Riemannian geometry associated with them, and also about certain quotients. That will be quick to address. So I will kind of imagine we have we start with a compact manifold, M, and yeah, I make it compact because then it's a little bit easier to work with. We can also say that it has no boundaries and make it even easier. And I'm looking at the space of diffeomorphism, smooth, invertible maps from M to M. And this space has a natural group structure. If I take two elements, phi and eta, I can multiply them. How do I multiply them? I just compose them with each other. It gives me a new diffeomorphism. Yeah. C infinity at this point. Yeah. Yes. So C infinity, and the point here is that you want to think about, so this is a manifold, compact manifold, okay, finite dimensional. You want to think of this also as a manifold, and in fact a little bit more, you want to think of it as a Lie group. Okay? And you can do this, there is a rigorous way of doing this, and one way of doing it is that you model it as a manifold on a Frechet space with functions. So I'm not going to talk much about these details, but let me just say that when I think of this as, and when I say that it's a Lie group, I mean with respect to this infinite dimensional structure. And if you do it like this, then the group operations will be smooth. There are other ways of doing it, which are kind of sometimes better from the point of view of doing analysis, like using Banach manifold structures, but then you lose this Lie group structure. You lose some of it. Okay, so I want to think of this as a manifold, and what is then the tangent space of this manifold? So let's say I take some diffeomorphism phi. It takes points in X and maps them to other points phi of X. That. Then I take a kind of variation of the function. This is, again, a little bit vague. So I take some variation of the function, and then I keep this point fixed, but I vary this one, then this point will move around infinitesimally. So it's a vector sitting above that point. So that means that if phi dot is an element in the tangent space, we can think of this as a mapping that takes points x in the manifold and gives me vectors, but not vectors sitting above x. It's not a vector field in general, but vectors sitting above the point phi of x. Okay? So this will be an element phi dot of x. The dot here just means that it's a tangent that kind of sits here in the tangent space m above phi of x. And in the particular case where my phi is the identity mapping, just taking x back to itself, then of course this mapping will be a vector field, a smooth vector field. So that means that the algebra corresponding the algebra of this infinite dimensional Lie group would be the space of smooth vector fields. These are smooth. And of course, you know, if you have this group structure, it induces some bracket structure as well. So what is the bracket structure? What is little add v acting on w to vector fields? Well, this would just be the vector field bracket. Okay. So that's the first thing. Have the manifold structure, this group. We have the group structure as well. And eventually what we want to do is to discuss, induce a Riemannian structure. It will be a weak Riemannian structure with respect to this. Okay? At least some Riemannian structure on this space of diffeomorphism. That will give us a connection to fluid dynamics. So before we do that, let me just say something. We can look at a subgroup. So far I didn't induce any structure on M. It doesn't have any structure, but assume that I have a volume form on M. You can call it mu. Then I can look at the subgroup of diffeomorphisms that preserves each little volume element. That would be the volume preserving. This subgroup of volume preserving goes the diff mu of M. So now I kind of put some structure on the manifold, so it has a volume form. Then I look at all the diffeomorphisms. Serve this form. And this, in fact, is also a Fisher-Rao Lie group. In fact, you can even give it a little bit more structure, technical thing. It's called a tame Fisher Lie group. And the good thing in that category is that then there's a Nash-Moser. Okay, so why did I bring up this subgroup? Well, for several reasons. One reason is that when we talk about the incompressible fluid equations, we will see that those equations correspond to geodesics not on the full space of diffeomorphisms, but on this subgroup of volume preserving diffeomorphisms. Okay? That's the one reason. The other reason is that once you have a group and a subgroup, you can take the quotients. And you can take it from the left or from the right, okay? And you get some quotient space. And let me illustrate this. And I think, or at least did talk about this a little bit as well, and that if you do this, you get a connection. You get something which is very relevant in our setting, namely probability densities. Okay. So here is the picture that goes along with this. Imagine this is now not finite dimensional manifold, but this is the space of all diffeomorphisms. The groups are somewhere here. We have the identity mapping. And then we take as a submanifold here, we take these volume preserving ones. If mu of m and now we're interested in this quotient. So we're interested in diff m quotient by diff mu of m. This should be equivalent to something. What is it? It turns out that this is exactly the space of smooth probability densities. That's a result of Moser, 1965, I think. And how do you see this? Well, so the projection then corresponding to this identification. The projection is depends. You can do it on the left, taking left cosets or right cosets. Always forget which one is which. But I know which projection I want. In this case, I want the one given by pullback. Sometimes you want push forward. In this particular case, I want pullback. So I take some diffeomorphism. And from that, let's call it theta. And from that, I get a probability density. Probability densities. By acting with this diffeomorphism on some reference u. Now I'm assuming that this is already a probability. Okay, so then this will be an element of M, because the total volume is preserved when you act with the diffeo. The total volume is always preserved. It means it takes this identity fiber and maps it exactly to the mu, but you also get the fibration space. So each of these fibers maps to single elements here. Okay. And in fact, it's a little bit more than this is true. In fact, this is a principal bundle, an infinite dimensional principal bundle structure. I probably Peter knows much more about this, but I think this is a result of Hamilton, or at least he has it in. Notes about Fisher-Rao V groups. And that is a little bit complicated to prove that you used Nash Moser. So, but this is a very nice construction. It's an infinite dimensional principal bundle structure, which means that each of these fibers are parameterized by this subgroup of volume preserving diffeomorphisms. All the projections are smooth and so on. So that's a beautiful structure, and it's a central structure, and you can do it either with this map, the pull back, or with push forward. And in the smooth category of fresh air, it works in both settings. Okay. And maybe I should say something about this choice here of pull back and push forward. Because what we want to do now, which will be kind of the central theme here, is that we want to induce various metrics on diff m. Okay? We want to induce a metric which is such that it's invariant under the action of this subgroup. Because if it's invariant under this action, it will descend to a metric down here. Okay? And then we want to kind of think of this in terms of information geometry, because then, remember from Ali's talk, then we have a natural metric down here, the Fisher-Rao one. This unique Riemannian metric, which is invariant, okay, with respect to the action of the group from the other side. Because you kind of think you think about it like this. You use here the quotient to get cosets, but then you still have an action on this space by acting from the other direction, right? So that means that you can talk about the metric being invariant with respect to that action. The Fisher-Rao metric is the only one. But there are, of course, other metrics, non-invariant metrics, that also come in this way. And one of them is the metric, the Riemannian metric associated with the Wasserstein 2 distance. And when you talk about that one, then it's more natural to look at push-forward actions here. And that gives us also a kind of encapsulating this geometric framework from the point of view of with a very smooth transport. Yeah. So whatever structure I'm interested in, I always want it to descend with respect to this quotient here. Yes. Okay. So not necessarily. Not necessarily. The important thing for it to descend is that it's invariant with respect to. And in fact, if you talk about optimal transport, it's not going to be fully right invariant. It's not going to be fully invariant. But when you talk about information geometry, it is going to be fully. In some sense, there's more structure there. There's more kind of canonical structure in information geometry than in optimal transport. Okay, so let's continue. So far, I didn't say anything about well, I did talk about Riemannian metrics, but I didn't specify them. So now let's say something about Riemannian metrics. We keep this in mind, this projection and the quotient, but now I'm going to focus, on the group. Be it either the full group of diffeos or the subgroup of volume-preserving diffeos, or just some group, some Lie group. Okay, so let's talk about Riemannian structures. Riemannian structures, Lie groups. So there is a picture associated with this as well. So here Now I just want to give you kind of abstract construction. So let's assume we have a Lie group G. Has some identity somewhere. And we want to assign a Riemannian metric to this Lie group. So what does it mean? It means that on each tangent space, we need to specify an inner product. If you take some element here, G has a tangent space, there's a natural way to construct kind of inner products on a group because you have the group structure. So you can take a vector on any tangent space and you can act on it. The group acts on itself. You lift that action, it's going to act on its own tangent vectors. Then you can take this vector, let's call it capital V, and you can translate it to any other tangent space you like. In particular, you can translate it to the tangent space at the identity, which is the Lie group, Lie algebra, okay? And then you get some, which is then V, then action you can choose if you want the action from the left or from the right. Okay, I'm going to use action from the right because that's what gives us a kind of hydrodynamics. So I act with the G inverse on this one, lifted action, and that gives me a vector in the algebra. Okay. So now that means that if I want a Riemannian structure, I can say, okay, it should be invariant with respect to this right action. So that means I only have to specify one inner product, for example, at the Lie algebra. So I construct a Riemannian metric like this. So I take two tangent vectors, W, V and W, which is in the tangent space of some point G in the group. And then I define their inner product, the Riemannian structure, this way. So the Riemannian tensor applied to these two vectors at the point G is going to be given by some inner product on the Lie algebra for the translated tangent vectors. So this is all I have to specify. Inner product on the algebra G. So this is the class of metric that I'm for now, because I got the question. Okay, so this will be a fully invariant or fully right. In fact, sometimes I'm only interested in metrics that are invariant. But for now, let's take this picture. And then once you have a metric, what's the next step? Well, then you want to know what are the geodesics. So now let's discuss geodesics. Want to know what the geodesics are, but what you do is you write down the geodesic equations describing the geodesic. Okay? And in this particular case, when you have a setting like this, these equations are called the Euler-Arnold equations. Why are they called like that? But Euler, because in fact, in a particular case, when G is the volume-preserving diffeomorphism, and you take the inner product at the algebra, which then would be divergence-free vector fields, you take that to be just the L2 inner product, then it turns out that this geodesic equation that you get is directly described by Euler's equations. Okay? And Arnold, because Arnold was the one that explained this. Yeah, sometimes, but in general, no. Sometimes you can take, if you're a finite dimensional compact Lie group, for example, you can take minus the killing form to be your metric, and that is then going to be a bi-invariant metric, and that metric is such that the Riemannian exponentials exactly. There's a problem with the exponential map in infinite dimensions, which is that it doesn't cover the identity, this diffeomorphism. But you can construct, it's easy to construct the Riemannian exponential map that covers the identity. So in a way, that's better than the group. Anyway, so Euler-Arnold equations. And what do I have to do? Well, so to get the geodesic equation, I can use this relation between Riemannian geometry and Lagrangian mechanics. So I think of the geodesics are described by solutions to the Euler-Lagrange equations for a Lagrangian consisting only of kinetic energy. This kinetic energy is defined then by the metric. Okay, so and then I take kind of paths where I fix the endpoints of the path. So let's say I take the first one to be the identity. It doesn't have to be, but in fact, since everything is right invariant, I can always choose it to be. And then I take some path here. So this would be G1, then I take G of T, some path here. And then I want to give conditions for this path to be geodesic, and we know that it's a geodesic if it extremizes this kinetic energy Lagrangian. So if I write this in formula, what I want is that I take the variation of such a curve. I take the variation of the action functional 1/2 times the integral, let's say from 0 to 1. I'm running from 0 to 1, and then I take my Riemannian tensor, and I take the derivative g dot of my curve, plug it in there. This is a Riemannian tensor G. Everything time dependence with respect to this. Okay? And I want to extremize this. So if I take the variation of this thing, I'm going to get something like the 1/2 goes away, and then I have integral 0 to 1, and then I have here the variation, because, yeah, what's the first thing I can do? First thing, before I take the variation, I keep that outside here. Let's just use the fact that this is right invariant, okay? So I translate everything back to the identity where I actually know what the is. And then I get G dot G inverse, G dot G inverse, G dt. Thing. Now I take the variation. Happens, I get the integral 0 to 1 metric thing, so I can take it just the variation of G dot G inverse, and here I have G dot G inverse. Let's call this D. dt. Now, before you can continue, you have to ask, okay, so if I take a variation of my curve, this variation is described infinitesimally by some curve in the algebra. You can always do that. Then you can for matrices it's very easy. It's maybe in general it's a little bit more complicated, but you can see that the variation of this thing inverse is given by the following formula. So if the variation is generated by, let's say, let's see what I used here, by W, then this is going to be W dot plus, and then V, which is the V here, V commutate or Lie bracket with W. Calculation to show that. And once you have that, you can continue. Now we go from here and we continue. What do we have? Then we have an integral 0 to 1, and we now know what this variation is. It's W dot plus this V, which I write just as add V on W, then in a product with V. E, okay. Now, what do I want to do? Well, I want to isolate, the variation was generated by W, remember? So I want to isolate the W and use a fundamental lemma of calculus of variation to get an equation. So how do I isolate the W? First, here's a time derivative. I can move that over there. I will get something like this, W here, and then I will, when I move the time derivative, there's a minus here. I don't have to care about the boundaries because I'm fixing the points there, so the variations are going to be 0 points. And then what do I do with this thing? Well, let's just do it formally. Okay? So we take the transpose of this mapping with respect to the product. Okay? We call that add transpose. Then we're going to get minus the plus, of course, if I just define it like that, add the transpose now with respect to this inner product acting on V. It could be true for any variation. Which means that I have my equation, just put this equal to 0, because I want the variation to be 0 in order to extremize the Lagrangian. So then I get that V dot is equal to add the transpose add to I think I made an error, sign error. I think actually if you do this calculation here, have here, here, and of course the only way to really know is to sit down and do it. Yeah, so I'm saying like this: we take a variation of the curve G of t, okay? And because we're on a Lie group, we can always generate that variation by, well, at least in finite dimension, by some generator in the algebra, okay? So that would be a time-dependent path as well, but in the Lie algebra. That's my W. That's my W of t. I'm skipping over some details here. So if you like, this is the relation between this variation and so that's nice. So somehow, you know, computing the geodesics means that we have to solve this equation. This is what is called the Euler-Arnold equation. But of course, this doesn't give us the path in the group, and I mean, we expect to get the path in the group. But we know from the definition of V here how to get this. So once we solve this equation, we have a time-dependent generator V, Then we can integrate that according to this equality here. And we get that G dot is just V. This is now time dependent. Acting on this. This is an ODE that you have to solve to reconstruct the actual geodesic on the group. And the beauty of this thing here is that if you talk about hydrodynamics and you take this group to be diffeomorphism, then these equations just can be interpreted as Euler-type equations, the equations describing a vector field. So that's the kind of beauty of this framework. You can also, there are also kind of interesting finite dimensional examples. One of the simplest examples that you always see is you take the group to be just SO3, rigid rotations in 3 dimensions. And then you take your metric to be some kind of inner product defined on the algebra. And you identify the algebra just with R3. And then the Lie bracket will be just a cross product on R3. Then you write down these equations, and what you end up with is, again, the Euler equations, but the Euler equations for a free rigid body. That's the first example. The second example is infinite dimensional. Then you take G to be this group of volume-preserving diffeos. You take the right invariant metric to be the one corresponding to L2 metric on the space of divergence-free vector fields. So in order for this to work, L2 requires, on vector fields, requires the Riemannian structure. So here you have to kind of start with Riemannian structure on your underlying manifold M, okay? And from that, you construct this L2 metric, and you write down these equations. Because you're on a subgroup, you need to take care of actually projecting back. You know, when you do these variations, you need to make sure that you land in the right space, which is how pressure comes up in the Euler equations. And the other term is the material derivative term that you have. So that's a kind of the 2 main examples, if you like. I'm going to, let's see, going much slower than I expected. I'm going to give you maybe some more examples related to what Alice was talking about. Yes. Oh,
problem
No. The Euler equations require a metric. The covariant derivative in there. Yeah, yes. So just for reference, let's write down the Euler equations. So we have V is now a divergence-free vector field, and then the Euler equation would be V dot covariant derivative V on V. Here is where the Riemannian structure comes in. This is equal to minus grad of P. This is kind of projection to make sure that you land in the right algebra. That's the example. But let's take another example now. So let's take this example that Liz was already talking about, the Hunter-Saxton equation. Okay? So, Saxton. This was a model know, formulated, I suppose, by Hunter and Saxton. I think it describes some director field. I don't know the original. But I do know about the geometry of this model because it's very, very beautiful. And in fact, it has even more geometry than this, and it's connected to Fisher-Rao, as we will see. But for now, let's just think of this in terms of Euler-Arnold equation. So what is the group? We take the group, the Lie group, to be a space of diffeomorphisms. We take all diffeomorphisms of S1. Okay? This, if you pick here, this would be the periodic contrasection. So that's one thing we need. And then, of course, the corresponding algebra would be vector fields on smooth vector fields on S1. And what else do we have to specify? We have to specify this inner product on the algebra. So given two vector fields u and v, I need to specify this inner product. What is it in this case? Well, I just take. So here I'm using a little bit more structure. I'm using a volume as well. I'm using a Riemann. I'm differentiating as well. So let's just write it like this: u x. These are derivatives with respect to variable in S1. So if you think about it carefully, you see that it's not really an inner product at all, because it has a kernel. To do this but the kernel in this case is quite small. Right? It's one-dimensional, rigid rotations. In fact, you can make this sense out of this by taking a quotient here, and then you're not exactly in a group, but you're a homogeneous space, and there's a whole theory about that. But for now, let's sweep those details under the carpet for a bit and think of this just as if it was a group, and then after we can check that the whole thing actually descends. By the way, this quotient would be the simplest case of the one up there. In one dimension, the volume preserving diffeos are just. Okay, so what is the next step? Well, we have to compute this add transpose. Okay, so let's do that. So we take some test vector W, and we know the definition of add transpose of let's say U applied to V is the following. So when I pair with this in the inner product, this should be just add U applied to V, W paired with V. And this here we know everything. We know what this is. Okay. So what is the bracket in this case? And it's just U x V minus Vx U for minus sign error. Okay, yes. You're right, yes. Okay, so let's work out the minus signs as we go. Yeah, exactly. Okay, so now let me do this calc. I wanted to do it carefully. Let me do it a little bit quickly. So what do I do? Yeah, you see what happens. You have derivatives here. You have to do integration by parts, moving derivatives so that you isolate your v, and then you read off what you get here. Okay. And when you do this, oh, okay, now that I leave that as an exercise. what you see is that actually you don't immediately get add transpose from this. Okay? But what you see if you think about it is that if you take minus add transpose u on itself, okay, and then you add two derivatives. And there's no coincidence that we do it with minus, because minus and then two derivatives actually corresponds to kind of representing this inner product in the L2 inner product. So we think of this as the inertia operator associated with this H1 or H1 dot inner product. And then you can read off what this is that you get by doing this integration by parts. And then you will see that this is actually equal to minus 2ux uxx, then minus u with three derivatives times u. And then you just take this equation and you apply the inertia operator on the left-hand side and on the right-hand side. Then on the right-hand side, we have exactly this thing, which we know what it is. And on the left-hand side, you just have to apply something here, which is minus two derivatives. And in the end, this gives us, what we do is we take u dot plus add transpose uu, and we add these two derivatives. Here we don't have to care about the minus sign. What we get is utxx. That's so ut here is the time derivative, okay? Plus whatever I had here. 2ux x plus uxxxu. And this, ladies and gentlemen, if you put this equal to 0, this is the periodic Hunter-Saxton equation. A little bit sketchy, but maybe at least you get some flavor for how you do kind of derive these equations. So it's nice. So this particular PDE, which is an integrable PDE, in fact, it's very easily write down what the geodesics are. This connects to what Liz talked about, but I will think I will touch more upon that tomorrow or next talk. For now, it's enough to say that just this equation has this Euler-Arnold. You see the game here. The game is kind of, we have a framework, an abstract framework for how to kind of get equations. And then we can take equations that we know have some sort of Hamiltonian structure and ask, the reverse question: is there a group and like a group of diffeomorphisms and some metric so that this equation fits into this framework? Okay. That is what we sometimes call geometric hydrodynamics, that game. There are plenty of equations that fit into this. So Kamasa-Holm is another one. All the various versions of Kamasa-Holm, most of them fit into this framework for H1 type metrics. And sometimes you need just a group of diffeomorphisms. Sometimes you need to extend the group a little bit to take care of the extra constants in the general Kamasa-Holm equation. And then you have to do these so-called central extensions of the Lie algebra, the corresponding group, to actually fit it into the framework. It still works. KDV is another one where you also have to extend the group of diffeomorphisms. Fisher-Rao extension, and then you get the KDV equation. So let's see, I have 10 minutes left. Maybe just to finalize, I should say something about the Hamiltonian formulation of these things. Hamiltonian formulation. Because so far, what I did, even in the derivation, was kind of from a Lagrangian point of view. This is natural when you start with Riemannian geometry and think about geodesics. You know, they extremize some length functional, some action functional. But there is also a Hamiltonian formulation of this, of course. So, and if you think about it geometrically, what is it? Well, when you have a Lagrangian formulation originally, then your phase space would be just the tangent bundle. But then somehow we have an invariance in the system of our Lagrangian, which means that the dynamics kind of can be reduced to some dynamics on this quotient, and this is what you identify. Algebra, by right translation. This is a kind of Lagrangian description. And there is a corresponding Hamiltonian description, because as soon as you have geodesic equations here, you can think about the Legendre transform and take your Lagrangian formulation into a Hamiltonian formulation. So if you do that, then phase space would be the symplectic structure T star G, so the cotangent bundle of G that has a canonical symplectic structure. You still retain the symmetry, so you reduce this, and what you end up with, then surprisingly, the dual of the algebra. And you can ask, here we have the symplectic structure, what happens to the symplectic structure here? Does it survive here? Yes and no. Yes, it survives, but you don't get, you get it in terms of a Poisson structure. That Poisson structure in itself is, as every Poisson manifold, it's foliated into symplectic. Those are called, in this case, are called coadjoint orbits. So, and you will always remain on these coadjoint orbits, which is the explanation for why you have a lot of conservation laws in some of these equations, like the 2D Euler equations you have infinite. Those are just the functions that are constant. Okay, so now I'm skipping a little bit, but if you do this story rigorously, you see that, well, maybe I should just write down what the Poisson structure is, because if you take the dual of any Lie algebra, there's a natural Poisson structure called a Lie Poisson structure, and to write it down, I have to specify, take two functions now on this space, G star, two functions f and g, and I evaluate them at some point m in G star, okay? And then what is it? It's going to be the natural pairing between these dual elements and the brackets between df evaluated at m and dg evaluated at m. Notice that we're here, we kind of take d of a function on G star, so that will be on G star star, which we identify with this is completely natural. And if you take the system that was described by this Lagrangian form of the Euler-Arnold equations, you get a corresponding Hamiltonian formulation, let's say in terms of this variable m, and it would then be just m dots equal minus, not add transpose now, but add star, which is the adjoint action of the algebra on the dual of itself. Called add star, and you have to write it. So in order to get the kind of generator here, you have to get some D group element. In general, you get that by taking D of the Hamiltonian. apply this to M. And in this particular case of Euler-Arnold equations, the Hamiltonian is quadratic, and it's described by one of these inertia operators. So this would be just, in terms of the inertia operator, this would be A inverse applied to M. So A is the inertia operator, it means it goes from G to G. Yes?